P are elements of a field. Such as infinite fields, like the rational numbers, the real numbers, the complex numbers. A real kind of a one-sentence way to describe what a field is, it's a set that's closed under addition, multiplication, subtraction, and division, even though the technical definition involves about 11 axioms, depending on how you count them. But, it's kind of like the rational numbers were the first time we had a field, where we could add, subtract, multiply, and divide without needing the step. And then but we'll also talk about finite fields. And we'll talk about what characteristic means a little bit too, if you have an idea what that is. So there's also a constraint on A and B, so that this is not 0, and that's required so that you have a tangent line that's well defined at every point on the curve. And also, that'll also give you 3 distinct x-intercepts when we graph something like that. And so, okay, one thing that's very handy with this is anytime you have a point, x, y, that satisfies this equation, then you have another one, unless y is 0, x minus y, because this is symmetric about the x-axis, because if you square a positive number, say you have a point where that y is one of your y values, if you have the negative of that, you'll get the same thing, because if you square -3, you get 9, all right? If you square +3, you get 9. So, so that automatically, once you know one point, you can get another point. So here's an example. So here's y squared equals x cubed plus 3x, minus 3x plus 7. So check to see if this point is actually on this curve. So if you plug 2 in for x, you would get 2 cubed is 8 minus 6 is 2 plus 7 is 9. And if you plug 3 in for y, if you square 3, you get 9. So you get 9 on both sides. So 2, 3 makes the equation true. So that's going to be one of the points. And you actually can see it here. If you look, 2, 3 is about right here. All right? Okay. So here's what we'll do. Here's kind of goes back to using the tangent and secant method to find other rational points. So 2, 3 is a rational point because rational numbers are numbers you can write as fractions of whole numbers or integers. They can be negative too. Integers mean whole numbers that are negative, and so that includes the positive integers or integers because you can write them over 1. Okay, so let's take the equation for the curve. Now here's where we have to do a little bit of calculus, because in order to add p to itself, we'll call that point 2, 3 p, we have to use a tangent line at p. And so here's where we need a little bit of calculus. So if you take the derivative of this equation with respect to x on both sides, you would take 2y times dy dx, since we're taking the derivative with respect to x on both sides. And so these are derivative rules you'll learn in calculus, calculus 1, and you get 3x squared minus 3. The constant just goes away, it becomes 0. But this is what you have to do, and then we'll solve for dy dx, and that's not so hard because all we have to do is divide both sides by 2y, and that gets dy dx by itself. And this, okay, so the derivative of a function, it tells you the slope of the tangent line at any point. So if we plug in our point 2, 3, that'll tell us the slope of the tangent line. So if you plug in 2 for x and 3 for y, we get 9. 12 minus 3 is 9, and 6 in the denominator. And that reduces to 3/2. So now we can write an equation for the line, because we have our point, 2, 3, and then the slope. And here's where we're using college algebra techniques that we did even the first unit. This is the point slope form. We plug in the point 2, 3, we plug in the slope here, and that's a variation of the slope formula. Now if we solve for y, you distribute, you get 3/2 x minus 3, and if you solve for y, notice we have a minus 3 on both sides of here and here, you'll get y equals 3/2 x. So that's the line that's tangent at that point, 2, 3. So if you draw the line y equals 3/2 x, it goes through the origin, right? If you plug in 0 for x and y, it's true, you get 0 on both sides. But notice that's perfectly tangent to our point at 2, 3. Okay, so here's what we're going to do. Each time we use a tangent or secant technique, we're going to find the third intersection point. So 2, 3 is almost like it's a tangent point, so it has what's called an intersection multiplicity of 2, because the tangent's sort of crossing it twice in some ways. And so what we'll try to find is this point, that third intersection point. So what we'll do is we'll take this y here and plug that in for y here, and we'll plug that in, and that'll give us a cubic equation. So let's square that, 9/4 x squared, and subtract it over. And so here's what we can do. Well, we know that 2 is a solution to that because it corresponds to an intersection point. So this is one way of finding that third intersection point. I'll use synthetic division. And this is a short way to divide a polynomial by something of the form x minus c. And let's see, make sure I'm on there. Okay, I can't see the. Okay. So for a cubic polynomial, you got to put in 4 numbers. So if you have a missing term here, like we don't have one there, you'd have to put in a 0 because the process has to know that you're representing a cubic. And so this will give us this will help us divide this by x minus 2. So we'll bring down the 1. Here's the process. You bring down the leading coefficient, then you multiply. 2 times 1 is 2. Now what happens when you add these two? 2 and minus 9/4, what does that come out to be? So 2, common denominator, right? 2 is like 8/4, so we get what, minus 1/4? So now multiply again, you get minus 2/4. I'll go ahead and write minus 1/2. Now if you add that, you'll have minus 3.5, that's minus 7/2 as a fraction. Now if you multiply here, you'll get minus 7. And if you add here, you get 0. And so this number down here will always be the remainder you get when you divide by x minus some number c. And it also turns out to be the value you would get if you plugged in the number into the polynomial. That's really a neat thing about polynomials. So f of 2 should be 0, and that tells us that, that reaffirms that 2 is a 0. But then we have this tells us the quotient. Like, I'll tell you what I mean by that. So we would know our cubic is equal to x minus 2 times x squared minus x over 4 minus 7/2. So these are the coefficients of the second degree polynomial. Now, since 2 has a multiplicity, intersection multiplicity of 2, then we should be able to divide by x minus 2 again and get 0 again. So let's see, bring down the 1, multiply. 2 times 1 is 2. What's 2 and minus 1/4? The common denominator again, right? That's 7/4. 7/4. Multiply by 2 again, you get what, 7/2? Now if you add, you get 0, and that's the remainder. So that tells you that if you divide this polynomial by x minus 2, you get a remainder of 0. And so that tells you then that our original polynomial is equal to x minus 2 squared times x plus 7 over 4. So one of the nice things about polynomials is if you have a root of a polynomial, and 2 is a root of this polynomial, a multiplicity 2, then x minus that number will be a factor of the polynomial. And actually in this case, it's a factor of multiplicity 2. Let me go back to the screen again here. So what this told us, that last line is x minus 2 squared times x plus 7 over 4. We got that from that last line in the synthetic division. That will, if you multiply that out, that would give you this polynomial here. So that tells you, so that's what it means for a number like 2 to be a multiplicity, have multiplicity 2 as a root. For a polynomial, that would mean x minus 2 would appear to the second power as a factor. It's actually a factor of this polynomial twice, right? Okay, so that's kind of the idea. But now we can find that third root. We can set the last factor equal to 0 and solve. We get x equals minus 7 over 4. Now if you plug that in, now we get the y value. Let's go back to that'd be the easy way. Don't plug it back into here. That'd be another way you could do it, but that'd be hard. Let's plug it back in here. And 3/2 times minus 7 over 4 is minus 21 over 8. and that's the y value for our new point. And so we have a new point, x, y, minus 7 over 4 minus 21 over 8. And these are, we can write those exactly as decimal numbers, right? So those are exact decimals. And that's the point down here. So here, but okay. All right, so we figured out this intersection point of this line, algebraically. Now we also get another point. If you go directly up where the x value is still minus 7 over 4 and change the sign of the y coordinate, that gives you another point. And that point's going to be important, and I'll tell you a little bit more later. So what we'll do next is we'll take the point that has the positive y values, minus 7 over 4, positive 21 over 8, and we'll draw a secant line between that point and our point 2, 3. Now, a secant line is simply a point between, it's a line between 2 points on a curve. That's all it is. Fancy word for a line that goes between 2 points that you know on a curve. So here's our other point with a positive y value. Okay, so we'll use this last point along with 2, 3 to create a secant line through these points. And for this one, we don't need calculus, right? Like on your last test, I gave you 2 points. I said find the slope and find the equation of the line between it. So here's the slope. Right, here's 2, 3, and minus 7 over 4, 21 over 8. So if you work that out, and I found it easier to multiply by 8 over 8. And that clears out these little fractions inside the compound fraction, the big fraction. So if you distribute, you get 24 minus 21. And if you distribute here, you get 16 plus 2 times 7 is 14. So you get 3 over 30, which is 1/10. So that's going to be the new slope of the secant line. And then we'll go back to the point slope form again. Use 2, 3. That was the easiest point. 2, 3, and 1/10. That's the point slope form, and multiply that out. X over 10 minus 20 over 10, add 3 to both sides, and you get this, and that's going to be, what, 28 over 10. But 28 over 10 reduces to 14 over 5. So that's the new line between those 2 points. So now, here it is. So here's our point that was a reflection of the intersection point through 2, 3. And now we want to figure out this point of intersection. Okay, that brings up a new point of intersection. So here's what we'll do. We'll plug that line into our, we'll go back here. Here's our line. Here's our elliptic curve. We'll plug that in there. We'll multiply it out. So we get this squared. You got to FOIL it out and everything. That comes out to be that and that. And now if we subtract and gather like terms and get everything equal to 0, that looks kind of messy, but I'm just subtracting all the terms, getting on one side, and that simplifies down to this. And we could do that same thing, use synthetic division, but there's another way. There's really a neat way to find out the other third intersection point. Because now we have 2 points and they're different. Last time we had 2 points, but they were the same. And, okay, so we use a different method this time to find the third intersection point. All right, so the fundamental theorem of algebra implies that a cubic polynomial equation with leading coefficient of 1, that's the coefficient of the x cubed, will factor as x minus a times x minus b times x minus c, where a, b, and c are the roots of the polynomial. If you knew the roots, it would actually factor, right? That's what I was saying about polynomials. If you have a root, say a, then x minus a will be a factor, and same with b and c. Okay, so when we multiply this out, we get what are called symmetric polynomials, but anyway, the coefficient of x squared is actually the negative sum of the roots. So if you know 2 of the roots, you just take the x squared coefficient, and you can figure out the third root. Well, that's going to be the x coordinate of that third intersection point. Okay, so the coefficient of x squared is the negative of the sum of the 3 roots. Okay, so if you know 2 roots of the cubic equation, which we do, you can easily find the third root. So here's our cubic equation we got after we plugged that secant line, that second line into the elliptic curve. We know the 2 roots, 2 and minus 7 over 4. Those are the x coordinates of the points of intersection, right? So we just set that with an unknown c equal to the negative of this coefficient here, the x squared coefficient, which is 1/10 when you take the negative, and then solve for c. So if we solve for c, we get negative 0.24 exactly. I'll write it as a decimal since it's an exact decimal. So if you plug in that, so we got the x coordinate. Now we just plug it back into the the equation for the line and work it out, and we get the y-coordinate. And I didn't approximate it. I don't like approximating. You know, this is the exact decimal form of that. So that's our third point of intersection there. Remember, it was real close to the y-axis, so the x-axis is a small and absolute value negative number. So there it is right there, minus 0.24, and the y value is like 2.76, so 3 would be about right here. And okay, so what we do now, we find another intersection point, is the reflection down here where y is negative. We just negate the y value again, and that gives us another point on the curve. Okay, so that's basically how the tangent and secant method works mathematically. Okay, so we'll come back to this, we'll talk more about that. But the tangent and secant method for finding rational solutions to polynomial equations, sometimes referred to as the rational points in an algebraic curve, dates back to Diophantus, and that was around, he lived around 250 AD, and he wrote the very influential book called Arithmetica, that a lot of mathematicians later on refer to. And sometimes he was called the father of algebra, right? I was trying to find that. It's hard to find that reference, but only 6 volumes of his Arithmetica survive today. Diophantus and Diophantine analysis is generally associated with finding rational solutions to polynomial equations in 2 variables. Okay? Various mathematicians down through the ages picked up where Diophantus left off and employed this tangent secant method technique, or a similar technique for solving higher degree polynomial equations. Like there was Bombelli in the 1500s, Francois Vieta around that time period, Pierre de Fermat in the 1600s, Leonard Euler in the 1700s, and then Carl Gustave Jacobi in the 1800s, and more recently Henri Poincaré. It was only with Henri Poincaré that work on the arithmetic of rational points on elliptic curves continued to present day without a break. So beginning with Euler and continuing with Jacobi and Poincaré, they tried to discover a way to define an addition of rational points on elliptic curves. And I think Euler's version originally had like integrals involved. Okay? And so an addition law may be defined whereby if P and Q are known points on the curve, and XY is a point of intersection of the line, just like we were doing, you have maybe 2 points, and P and Q might be equal, they might be not equal, then you can find that third intersection point. And what you do is you define P plus Q to be the reflected point, x comma minus y, which is why we were interested in that reflected point in the example. So if P does not equal Q, then the line is defined as the secant line between the 2 points, just the line between the 2 points. And if P equals Q, then the line is defined as the tangent line to the curve at that point. So there are some exceptions for adding points on an elliptic curve whenever the point at infinity is involved. So we'll talk about what it means to have a point at infinity, but it helps make the addition law works and helps make it into an additive group. And we'll talk about what that means. It might be an introduction to groups, but that's okay. This addition law creates a commutative or abelian group, and that the rules for adding points P, Q, and R on an elliptic curve, which include the point at infinity, satisfy 5 arithmetic properties or axioms. So first of all, closure. The sum of 2 points P plus Q is either a point on the curve or it's the point at infinity. For curves on the equation, we're only talking about elliptic curves with this form of the equation, the Weierstrass equation. So infinity can be thought of as a space above or below the graph of the curve, or the page upon which it appears. And then identity. For every point P, P plus infinity is P, so that point at infinity acts like the zero of the group. So you always have to have like an additive identity. And okay, so for a curve like this, a line through a point P equals AB and infinity, it can be thought of as a vertical line, and that would intersect also the reflected point, A comma minus B, we'll call it P prime, and that's the reflection of P across the x-axis. So after you cross that third point, and that's how we define the group law. P plus infinity would be A minus the negative of the other intersection point, which gives you back P. So P plus infinity is P. So that infinity does act like adding 0 to any point, gives you 0. inverses. For every point P, there exists a point on the curve, we'll call it minus P, for which P plus minus P is infinity. So the line through a given point P and this point, notice they have the same x-coordinate, so they'll lie on a vertical line. So any points with the same x-coordinate will be on a vertical line. So that's a vertical line. That'll intersect the point at infinity, either above or below the graph. And if you reflect that point at infinity, you go from above to below, or below to above, and you get back to the point of infinity. So that gives you the inverse of P denoted by minus P is A comma minus B, and so minus P is A comma minus B. All right, so people were trying a lot of different ways to define an addition law for points on elliptic curves, and it was okay. It was easy to come up with a way to add that gave you closure and inverses and identity. Those weren't too hard. What was hard was the associative law. Okay, so that's the last one to make it a group. So, remember what associativity of addition is. P plus Q in parentheses plus R is the same as P plus Q plus R in parentheses. So you can regroup and you still get the same thing. And so this method I'm telling you actually satisfies the associative law for addition also, but the proof of it it is hard to prove. It takes a chapter. Actually, it's more of a long section of the book. So that's hard to prove, and that was hard to figure out, because they were trying different ways to add points on a curve. And so this actually gives us a group, this method. So a group in general is a set with one operation that satisfies axioms of closure, identity, inverse, and associativity. Now, if it's also commutative, which ours will be, then that makes it a special group. It's called a commutative group, or an abelian group. Now, the proof of commutativity is real easy. It takes one sentence. The sentence is, since the line between P and Q is the same as the line between Q and P, it follows that the third intersection point x, y will be the same either way. And so when you negate the y value, you get the same point. So P plus Q will be the same as Q plus P. It's real easy, proof of commutativity. So when you have a group that's commutative, we can say it's abelian. So the guy who first started defining groups was a guy named Évariste Galois, lived in the early 1800s. And this is a case where the group consisted of functions from fields to itself, and the operation was composition of functions. And composition of functions is not commutative. And we'll talk about that later on in college algebra, composing functions. It's not a commutative operation, though. So these special functions satisfy the four properties of the group. The function composition is not commutative. Groups that are commutative are often written with the operation, you often write the operation as addition, because addition is always commutative in rings. So commutative groups are usually called abelian groups in honor of the Norwegian Niels Henrik Abel, and he also lived for a short time in the early 1800s. So both Galois and Abel didn't live very long in the early 1800s. All right, so in the previous example, let's talk about how we use the addition. With P equals 2, 3, then 2P was the reflection of this intersection point down here. It was the point up here, right? Now, if we do the secant line, 2P plus P, that gave us 3P. So 3P is 2P plus P, and that gave us the reflection of this new intersection point. So the 3P is down here, where x is negative, but not very negative, and y is negative 2.776. Okay. The third line between P, 2, 3, and 3P is given by this line. Okay, so now we're going to take 3P and P in order to figure out 4P. I'm actually, for this one, I'm going to skip the math. But you find the slope of the line between these 2 points, and then you use the point slope form maybe and figure out the slope of the line. So here's that line. It goes up and intersects way up here. And so that intersects at 4.89. Now here I did approximate. But I always use the exact values here, but just to get an idea what those points are. 4.89, 10.45 is up here, right? 4.89, a little bit past 10, you can see that. Now 4P will be the reflected point down here that I didn't put on the graph. So 4P will be this point down there. Okay, this shows that P plus 3P equals 4P. So let's explore a little bit. What if we added 2p to itself? If this was really an associative law, we should get the same point if we take a tangent line to this point. So let's try that. Here's our 2p. Here's the tangent line already written down. Now let's see. What would you do to find the? Oh, that's the line. Okay, that intersects the same point. It turns out. So showing that. Okay, I guess I left out the math of that one too. Okay, maybe we needed to do that. Okay, so this shows that 2p plus 2p gives you the. If you draw the tangent line at 2p was right here. So this green line and red line intersect right there at 2p. That tangent line intersects up at this point 4.89 positive 10.45, and then 4p is actually the same reflected point. So that shows this supports associativity because it shows that p plus 3p, which is p plus this, which is 4p, is the same as p plus 2p. So that kind of supports that it's associative. We couldn't do that. We couldn't say that 2p plus 2p equals p plus 3p if it wasn't associative. If it wasn't an associative law, we wouldn't know what we'd get if we tried that. 2p plus 2p could maybe be totally different than p plus 3p. All right, so elliptic curves over finite fields. Mentioned earlier, okay, so a characteristic of a ring with identity is the smallest positive number n that if you multiply anything in the ring, it'll make it 0. So that's another way of saying is you can only add anything in a ring n times to itself before you get 0. And you won't have that like with an infinite field, like the rational numbers. So those, they say, have characteristic 0. The only way to make it 0 is 0. So the infinite fields, rational numbers, real numbers, complex numbers, have characteristic 0. But the finite fields, a finite field will always have a size or cardinality equal to the power of a prime number, p to the k, where p is a prime number and k is a counting number, like 2, 3, 2 squared, 5, 7, 2 to the third, etc. And you can prove that using facts about vector spaces. Any linear algebra students here? Okay. So the cardinality of that type of field has characteristic p. It's always the prime number p. So every finite field has prime characteristics. So if you take anything in a finite field of size p to the k and add something to itself p times, you will be at 0. That's what a characteristic means. So this curve is used when the characteristic is not 2 or 3. So we didn't use 2, 3, or 2 squared, or 2 cubed. There are more complicated equations that are used for those. All right, so here's an example. Let's take z mod 7, which is all the numbers 0 to 6. And here's a good way to understand modular arithmetic. Who's had a little bit of modular arithmetic? Anybody? You've had some modular arithmetic? Okay, so take the whole set of integers, positive, negative, whole numbers, and if you divide by 7, you'll always get a remainder that's between 0 and 6. So imagine each of these numbers as being a box containing an infinite number of integers, and we just write the numbers because it's easier to write. Sometimes we write boxes around them because they're equivalence classes. They actually hold an infinite. So all the numbers in here are all the integers that if you divide by 7, you get a remainder of 6. All here, the numbers if you divide by 7, you get a remainder of 5. And that's also true for negative integers. You could take, let's see, we could take, maybe do this real quickly. 17 divided by 7 is equal to what? How many times is 7 going to 17? Twice 14, remainder of 3, right? And so often this is written, if you clear out the fractions, you'd have 17 equals 2 times 7 plus 3. And so 17 would be congruent mod 7 to 3. So that's one way that you can write congruent mod 7 is that way. And so this ends up being like 0. And so what about negative 17? What do you think it would be if you divided by negative 17? Well, you always get a remainder that's positive, or maybe 0 to 6. But this you'd use negative 3, negative 21. What would you have to add to negative 21 to give you negative 17? 4, good. So the remainder would be 4. So the negative 17 is congruent to 4 mod 7. While positive 17 is congruent to 3 mod 7. So these would be in different boxes, different congruence classes. All right, anyway, that's probably enough of that. Okay, so we'll use this curve, and that also it makes the discriminant non-zero, because A and B are both 1. Okay, so here's how we'll find points. We plug in 0 for x here. 0 cubed plus gives you 1. Plug in 1, you get 1 cubed plus 1 gives you 3. 2 gives you 2 cubed plus 2 is 11. What happens if you divide? Well, here's another way you can find out remainder. You can see how many 7s can I subtract from a number that's bigger than 7 until I get a number from 0 to 6. So if you plug in 2 here, you get 11. But 11 minus 7 is 4. So the remainder would be 4. How about 3? 3 would give you 3 cubed, 27, plus 30, 31. But 31 is just bigger than a multiple of 7, 28. And so you could subtract 7 4 times from 31 and get down to 3. And 4 cubed, and you can also do it as you go. 4 cubed is 64. Let's divide 64 by 7. That would give you 63 plus 1. 63 is a multiple of 7, so you have 1. Now let's add 4. 1 and 4 and 1 is 6, so you get 6. So you can actually, taking the modular, reducing modulo 7 commutes with all the additions of operations of arithmetic. So 5 cubed gives you 5. What would that be? 5 to the third, 125, third, 131. But let's see, 131 would be, was 14 from 140. Is that right? Now 126 is a multiple of 7. That's 18 times 7, right? And so, no, that's not right. Anyway, that turns out to be 5. And we plug in 6 here and reduce it down, divide whatever number you get divided by 7 and take the remainder, you get 6. All right, now what if we do with the y values and start squaring? We get 0, and 1 squared is 1, 2 squared is 4, 3 squared is 9, but 9 minus 7 is 2, 4 squared is 16. You can subtract 7 twice and get 2. 5 squared is 25, and that's 4 above a multiple of 7, so that would be 4. 6 squared would be 36, and that's 1 above a multiple of 7. 35, 5 times 7. So y squared would be this. So now we've got to match up the y squareds with this, because that's how we satisfy the equation. So it turns out the points we get are when y squared are 1 and 4, because over here we get 1 and 4, but we don't get any 3s, right? And over here we don't get any 2s. So the points we get using x and y values would be 0, 1, 0, 6, 2, 2, and 2, 5. So we just get 4 points plus the point at infinity. And, okay, so how would you add? So here we can't draw it, though. We can only draw for over the field of real numbers, but we still use the same method. So 2 times 0, 1, you find the tangent line through 0, 1. So you take your equation, and did what we did at the very beginning with the implicit differentiation. You use the derivative rules and take the derivative with respect to x on both sides, and you take y prime and solve, and plug in 0 for x and 1 for y. And that gives you 1/2, but we're looking for the multiplicative inverse of 2. And that turns out to be 4. Why is it 4? Well, because 2 times 4 is 8, and 8 is congruent to 1. So the way you divide out by 2 is you multiply by 4. You know, you want to be able to divide. And this is a field, so we should be able to add, subtract, multiply, and divide. Okay, so now let's use our point slope form. Plug in 0, 1, same thing. Our slope is going to be 4, so that's what we got for the derivative. And if we work that out, we get y equals 4x plus 1. Okay, so now we got our curve. We plug that into our curve again, multiply out. 16x squared plus 8x plus 1. But we can reduce as we go. What's 16 congruent to mod 7? 16 is bigger than 7, right? So what do you get if you divide 16 by 7? What's the remainder? You get 2, right? You can subtract 7 twice and get 2. What about 8?
1.
It's 1. Good. So those will reduce down. You can do that as you go. Now let's subtract over like we were doing. Oh, the x plus 1 will totally subtract. And now this one we can totally factor, right? We can just take out x squared. And x squared is a multiplicity 2, 0, but that makes sense because we started with a tangent line at 0, 1, right? and then the other is 2. So we actually can solve this by factoring. X equals 2 is our other third intersection point. You plug that in, you get 9, but 9 reduced modulo 7 is 2. So our point is 2, 2, but 2 times 0, 1, then you reflect to get what 2 times 0, 1 is, but 2 comma minus 2, so the intersection point is 2 comma 2, so our value is 2 comma minus 2, but that's the same as 2 comma 5, because you can add 7 and get, that's another way you can divide integers by 7 and get the remainder. So 5 and negative 2 are congruent modulo 7. If you take their difference, 5 minus negative 2, you get a multiple of 7. That's actually how congruence is defined. Okay, what about 3 times 0, 1? Okay, so now we find the secant line between 0, 1 and 2, 5, because that's what 2 times 0, 1 is. So we're adding these 2 points by finding their secant line. Now if you take the slope, 0, 1, 2, 5, so this is the old slope formula, minus 4 over negative 2. Now I wanted to divide and just give me 2, and I thought, well, maybe that's how I think about numbers, I need to be careful. So I added 7 to both of these. Minus 4 is congruent to 3. Add 7 to negative 2, that gives you 5. So it's 3/5. So I need to find the multiplicative inverse of 5 to the negative 1. And that turns out to be 3, because 5 times 3 is 15, and 15 is congruent to 1 modulo 7. So the slope is actually 9, which is 2. So the slope is 2. It's hard to follow, I know, because you have to totally relearn how to do arithmetic. I know. So if you all right, so the point slope again, we put in 0, 1, and the slope is 2. That ends up just giving us 2x plus 1. And now we can try again and plug that in and work that out and reduce down. Now this one is where I used the other trick, where the sum of the roots will be the negative of negative 4. So we have 4 equals 2 plus 0. Because remember, we're going through points with x values 0 and 2. And if you solve for x, you get 2. Plug in 2, you get 2, 5. But 2, 5 gives you, that's the third intersection point. So 3 times 0, 1 is 2, negative 5, which is the same as 2. If you start thinking, oh, we're coming back to other points, it's because our group is so small. We're going to come back to different points. So we get, okay, using these same techniques, you can show that 4 times 0, 1 is 0, 6. And so here are the points. If p is 0, 1, 2p is 2, 5, 3p is 2, 2, and 4p is 0, 6. So what about 5p? 5p, if you add 1p and 4p, then you're going to be on a vertical line going through the point at infinity, and you get, if you try to find the slope, it's undefined, right? 0, 6, 0, 1 is undefined, so we note that these points lie on a vertical line, so that means 5p is infinity, and that means the negative of p, the additive inverse of p is 0, 6. And so 2p plus 3p is also infinity. 2, 5 and 2, 2 lie on a vertical line, so they're inverses, additive inverses of each other. So if 5p equals infinity, one would say that p has order 5 in that group, the elliptic curve group. In any additive group G, if A is in G and n is the smallest positive integer for which na equals 0, then the order of A is n. That's a little bit different from characteristic of a ring. So any point q added to infinity results in q. So 6p would be p plus 5p, p plus infinity would just give you the same point back. So it starts over again. So this group, this elliptic curve group, cycles back to 0, 1. We see this group is generated by p equals 0, 1. So those 5 points we figured out were actually the only ones that we get in the group. So such a group, this group is actually cyclic because it's generated by one element. Of order 5. So this group with underlying field Z mod 7 would really be the same isomorphically as a group to Z mod 5 with regular addition, where the addition is not so complicated. It doesn't, isn't invited. So anyway, I need to move on here. But anyway, so if you change the equation, you'd have a group with 9 elements to x cubed plus 2. And, whoops. Uh-oh, I pushed the end button. I've done that before. All right, let's quickly get out of there. All right. All right, so if you kept the equation and changed the underlying field to Z mod 5, then you would have another group with 9 elements, but it's a different group with 9 elements. So the underlying field in the equation determine the elliptic group. All right, the discrete logarithm problem, an important aspect of elliptic curve cryptography lies in the fact that you saw how you could add a point to itself n times. That's kind of what we were doing back there. This lies in the fact that given a rational point p on an elliptic curve and the point q equals np, the positive integer n, it can be very difficult to find this n if you only know what p and q are. So this is an example of what's termed the discrete logarithm problem. So here's a multiplicative version of that. We have a to the x, where x is the exponent, congruent to b mod n. And this comes up in college algebra, where if you're working with real numbers, that's where a logarithm comes from. It's a solution to an equation like 5 to the x equals 13. You want to know, and you can figure out that that number is somewhere, the exponent you need on 5 to give you 13 is somewhere between 1 and 2. So that's where logarithm comes from. In the case of arithmetic on an elliptic curve, since we're adding points, the discrete logarithm problem becomes solving for n, giving points p and q. Okay, so, okay, this just repeats what we were saying, that any finite field, sometimes they're written s of q, and q would have to be p to the e elements, where p is a positive prime integer, and that's the, we had that before. All right, the reason why people are interested in using elliptic curves for encryption is that elliptic curves provide security equivalent to classical RSA public key systems while using fewer bits. For example, it's estimated that a key size of 4,096 bits for RSA gives the same level of security as 313 bits in an elliptic curve system. This means that implementation of elliptic curve crypto systems requires smaller chip size, less power consumption, etc. So in one test, a Palm Pilot by 3Com generated a 512 RSA key in 3.4 minutes, while in comparison it generated a 163-bit elliptic curve crypto system in less than a second. So less bits and less time. But what's a public key crypto system? What's an elliptic curve crypto system? Well, in 1976, Diffie and Hellman invented the public key cryptography, which revolutionized the field of cryptography, but also had a profound influence on the direction of research into computational number theory. The first usable public key system came about in 1977 with the RSA system, named after Rivest, Shamir, and Edelman. In 1985, Neil Koblitz and Victor Miller ushered in independently a second current of research in computational number theory by proposing an elliptic curve crypto system based on the discrete log problem of points on an elliptic curve. So in symmetric encryption, the decoding key can be ascertained from the encoding key. Like for an example, an old example is a code where you code a message by replacing each letter by the letter that appears 5 letters ahead of it in the alphabet. So you could take the sentence, Julius Caesar gasped, and you too, Brutus, and that would be encoded with, J would be replaced by O, and everything would, so it would become this, you know. But this can be solved with just, by staring at the numbers and figuring out where the vowels are. Every morning in Las Cruces, when I was a grad student, they had a crypto quip, where you just kind of look at, you can tell the words, and every letter was replaced by a totally different letter, and you know, you can visually figure out what the vowels are, and you can figure out what things are. So that's not very secure. In this situation, how does the sender get the key to the receiver without opening up the possibility that the key be stolen and the code then be broken? Another symmetric code would be to represent a message to be sent as numbers in a matrix or a set of vectors, and then use an invertible matrix to encode the matrix through matrix multiplication. And that would be symmetric, because the receiver, if you knew how to encode it, you could find the inverse of the matrix and then decode it. So that's, the code would be vulnerable. Now, in asymmetric encryption, in which the encoding key is public, in that case, the encoding key is publicly displayed. Since it's nearly impossible to ascertain the decoding key from the encoding key. The extreme difficulty of factoring very large integers plays an important part of the security of the RSA public key system. I'm going to maybe try to make that. I don't think anybody's there for its left. Okay, a coding system is a public key crypto system if each person has efficient, reusable computer algorithms for encoding and decoding messages, and 2, each person's decoding algorithm is not obtainable from his or her encoding algorithm in any reasonable amount of time. because that encoding algorithm is made public. It can put in like a phone book or something. Generally, public key systems are slower than good symmetric encryption systems. So therefore, it's common to use a public key system to establish a key. That's how you get the key over. And then use a symmetric system. The improvement in speed is important, because then if you're transmitting a whole lot of data, you might want to use a symmetric encryption scheme after passing along the key in an asymmetric public key way. So popular symmetric encryption methods include the Data Encryption Standard, DES, and Advanced Encryption Standard, AES. So let's say that Alice and Bob want to agree on a common key that they can use for exchanging data via a symmetric encryption scheme using DES or AES. So Alice and Bob could be banks that want to transmit financial data. It's impractical and time-consuming to use a courier to deliver the key. Moreover, we assume that Alice and Bob have had no prior contact, and therefore the only communication channels between them are public. So one way to establish a secret key is the following method. Alice and Bob agree on an elliptic curve E over a finite field F sub Q, such that the discrete logarithm problem is hard to solve in that elliptic group. They also agree on a point. So remember that this group is made up of points. That has a large order. Usually the point P and the curve E are chosen so that the order of P is a large prime. Alice chooses a secret integer A, computes A times P, and sends the point to Q, called Q to Bob, which is AP. And we saw how you make AP. That's where you're just adding P to itself. But that A is going to be very large, and so you have a computer do it. Bob chooses a secret integer B, computes BP, and sends R equals BP to Alice. So Alice computes A times R, which is ABP, and Bob computes BQ, which is BAP, which is ABP, because, multiplication of counting numbers is computed. Alice and Bob use some publicly agreed on method to extract a key K from ABP. For example, they could use the last 256 bits of the x-coordinate of ABP as the key. Remember, that's going to give you a point. Or they could evaluate a hash function at the x-coordinate. A hash function inputs values of arbitrary length, potentially billions of bits, and outputs values of fixed lengths, like 160 bits. Importantly, if someone, say Eve, was eavesdropping on Alice's and Bob's public interactions, Eve would only be able to see the curve E, the finite field S and Q, and the points P, Q, and R, but she wouldn't be able to determine ABP. Because she'd have to figure out, in order for eavesdropping Eve to determine ABP, she'd have to first determine A from AP or B from BP. Which means that Eve would need to solve the discrete log problem in the group. Okay, so here's a quick example of that. That's the end of the talk. The Elgamal public key encryption can be implemented in any finite group, provided that the discrete log problem is considered to be intractable. This is thought to be the case for groups on the here. This is a modification of a scheme by Menezes Vanstone. So we need a large prime P, an elliptic curve E over Z mod P, a point P and E, for which the discrete log problem is considered intractable. A positive integer K, this would be a key passed on earlier, perhaps using the method previously described. Q equals KP. So the public components, these are public, E, capital P, little p, and Q equals KP, and K is a secret. K is kept secret. So the message space would be in the non-zero elements of Z mod P. That's what the stars mean, it's the non-zero elements. So a message, M equals x1, x2, is encrypted as follows. So M is the secret message. Select a random positive integer C less than the order of P. Recalling Q equals KP, compute R equals CP. Then C times Q would give you a new point, Q1, Q2. Then you multiply Q1 times X1 and Q2, and then you reduce those mod P. We'll call those Y1 and Y2. And C can be chosen to avoid the unlikely possibility that either Q1 or Q2 is 0. So you send that message, which is this, R and Y1 and Y2, and the recipient encodes this as follows. First, the recipient determines Q and Q2 by computing KR. So KR is going to be K times CP. That's the same as C times KP, which is CQ. So they would just multiply this by the R that's coming in by the secret K, and that would give us the point Q1, Q2. And then you take the inverse, that's the multiplicative inverses we talked about, and multiply the y1s times those q1 inverse and q2 inverse, and that gives you back the message. Okay, now the message n is revealed. Okay, so here's some of my resources that I use. I think I use this one probably the most, by Lawrence Washington. Both these last two start out really kind of fun and easy, but they get kind of high level pretty quick. So, and this is a couple of chapters in this book I've used for modern algebra, has some things about elliptic curve cryptosystems by Norman Riley. And there's a lot of interesting history about Diophantine equations in this. It's kind of a thin book. I've actually read this whole book. I've only read parts of these books, but that's a really thin book. Anyway, any questions? That's my talk.